That's what happens next. And I'm going to drop you a link here in just a second. It just takes a second for YouTube to do its thing. Whoa, seriously, hot mic. Junlin, you got a hot mic. It happens to everybody. It happens to everybody. Okay, where are we at here? Oh yeah, I got all distracted. I was going for that link, and then I went crazy all of a sudden. I don't know what happened. Okay, here we go. Dropping the link. It sounded like airplane or wind, Junlin. Don't know, but it's all good. Okay, there we go. There's the link for right now. All right. Hey, welcome everybody. Welcome. Walter, there's that link for you. If you don't mind dropping that in, I'm most appreciative. Ooh, Junlin, seriously? That was just, oh, that's rough. That's really rough. Gotta say it. Okay, slides. Where are we? We're going von Neumann, right? We are von Neumannizing here like crazy, as I recall. What I didn't do, because I'm being just a little slow on the uptake, is go remind myself exactly which slide so I could be like drop right in and feel really cool. Instead, I'm just going to figure it out in real time like I always do and then not worry about being cool. My recollection, I think we've got some hot mic going on still. My recollection is that we were on this instruction processing. Yeah. Oh, yeah. I do remember this. Okay. Do we have any, Walter, is there any housekeeping, anything that we need to just say before we dive back in? Nope. All right. And anybody else, you got any other? I trust, from what I can tell, and by the way, while I've been recuperating, Zach and Walter, you guys, right from here, man, right from here. So appreciative of you two. Just kind of, I mean, I've been just so, it's been such a rough recovery, but anyway, this is the public acknowledgement that you guys have been solid gold. And from what I can tell, the DMQ is working, and what I trust, since I'm coming back around now, I'm off the narcotics, and I'm just saying no to drugs now, and coming around pretty quickly. Actually, I'm feeling a lot of like a real uptick in the recovery. So hopefully coming back, online better, right? Uh, if there's anything, kind of globally that you're struggling with or whatever, please ping me, okay? And again, I know there's a couple of you that are like, yeah, we did that. You haven't responded yet. I know, but I'm just saying that it's coming around, okay? And I'm going to be responsive. I feel it. And I think after this week, we got 6 weeks left in the semester. Does that sound right? That sounds really good to me, by the way. Love the summers. Okay, let's do it. Instructions. Okay, now let's see. Here's the idea. In memory is just bytes. That's it, just bytes. So those bytes can be anything. Well, one of the things that the bytes can be is an instruction. And an instruction, I mean, again, that you can look at any set of bytes, 8 bits, 16 bits. In the LC3, it's 16 bits, right? In every location in memory, there's 16 bits. You can look at it and you can interpret it any number of ways, right? You could say, oh, that's a 16-bit 2's complement integer. Or you could say, oh, that's a 16-bit unsigned integer, you could treat it that way. As a 16-bit unsigned integer, you could say it's an address. Sure. It could be pixels, values of a pixel. Could be any random anything that we decide that we want it to be. But one of the very, very important things that it can be is an instruction, okay? And I know this is just a little bit mysterious at this point still, and hopefully by the time we're done, it's gonna click at least. And I don't expect you to be, to come out of this thing and be computer engineers and, dig the circuit. Some of you guys dig the circuit stuff. That's great. Um, but I don't expect everybody to pop out with that. But you don't have to have that to succeed. I just want a little peek through. You're just going to peek and just see a little bit, behind the curtain of how this whole thing kind of rolls, and this notion of what do the bits mean. That's one of the big clicks that's going to happen. Okay, later on when you have the advanced architecture class, and then you have the compiler class, you're going to go deep down that rabbit hole. And when you pop out, there's going to be a clarity in your mind of all that interplay and all those levels of abstraction and how they all kind of click together. And that's going to be a very cool thing. And it is really, truly one of the neat kind of deliverables at the end of this whole curriculum as you work your way through and get this undergrad degree. But the first glimpse of that is here. This is the first. So I don't expect you to master it, just a little glimpse, okay? So don't be too hard on yourself if you're like, I don't quite get that. It's okay to not quite get it, frankly. As long as you can get it enough to function with it and accept a few things on faith until, the time that it kind of actually clicks for you. But this is a really key thing, and it was a very key deliverable in what became known as the von Neumann architecture, which is that data and programs are both just bytes in memory, and they can be intermingled together. They can be in separate chunks. It doesn't matter, but they're both in memory. And the idea here, and we talked a little bit about this, and I think we're going to come back to it. Well, we will come back to it, is this idea of a fetch, decode, execute cycle. I've said it like a bazillion times already, right? I have. The fetch, decode, execute cycle says that the circuitry of the computer, in this case the LC3, the control unit, running a state machine in circuitry, in hardware, there's a state machine, okay? And what does that state machine do? It looks at the program counter and says that's an address, 16 bits. Looks at that location in memory, right? Flips down, there you go, pulls that out, puts it into the instruction register, and then dices it up like a sushi table. Starts slicing the sushi. I love sushi. And then decides like, okay, what is that instruction? Why is it called an instruction? Because it instructs the computer what to do next. And then it just increments the program counter. So the program counter is ready, now pointing at the next instruction. It executes the instruction, grabs the next one on the sushi table. Slicey, slicey, slicey. What is it doing? Now I know what to do. You want me to move some stuff, add some numbers. What do you want me to do? And they're very tiny little instructions for the computer. And when you think about writing code like in Python that you've done in like 1400, 1410, you're going to do in Python for loops and if statements and things like that, right? They're kind of high level. They feel low level because you're programming, right? Because in our walking around as humans, we don't usually think that granular, about the world around us. Sometimes we have to, and we do. And then you get to Python, you feel like look how low level I am. Well, every one of those Python instructions, like if if color equals green, then, here comes what you're going to do. Like that one line, that might be like 5 or more assembly instructions. So the assembly instructions are even smaller, okay? And then it turns out, don't worry too much about this, but it turns out that every assembly instruction actually has down in the hardware even smaller chunks of little micro instructions that do even tinier things. And that's back to that abstraction. There's a reason we talked about abstraction, right? With the girl laying on the lawn at the Google, whatever, you know what I mean? And the abstraction going up and down. There's a reason we talked about abstraction, okay? It really is a critical idea that we have to just keep coming back to, okay? But for our purposes, so we're really going lower than Python when we get to assembly language. But just understand that there's even lower below that down in the hardware with these sort of, micro, we kind of think of them as like micro instructions. And we'll talk, and we'll touch that idea, but not expect you to, become the master of that, okay? But it is executed one instruction at a time by the control unit, okay? That's what we're doing. Now, this instruction that is stored in the computer, and then okay, somebody want to ask the question. I almost said somebody want to ask the dumb question. It really isn't a dumb question. It's there are dumb questions, by the way. Anyone who ever says to you, now there are no dumb questions. There are dumb questions, and we all know it, but that's not one of them. Okay. Um, Sorry. No, there's nothing else I'm going to say there that isn't going to get me into trouble. Okay. Or like more trouble than I already am or whatever. Uh, but the I think a great question at this stage of the game is still, how do I know that that's an instruction in memory? And you know what the answer to that is? Anyone want to drop a guess before I just give the spoiler here? How do I know that that's an instruction in memory? I'll tell you this, just by looking at the memory, I actually can't tell. I cannot tell just by looking at the bytes because it could be anything, right? I can interpret it a bunch of different ways. I don't know, right? And it turns out also that just about every random bit pattern, looking for some answers in the chat, it turns out that almost any random bit pattern can be intelligently interpreted as a machine instruction. So if I just randomly scramble memory and say, well, that's my program, go, and just start trying to execute it, it'll execute it. It'll execute the garbage. And it'll make no sense and it'll probably screw everything up. No respondos? This is probably a bad question. Yeah, there are dumb questions too, it turns out. that sometimes that the professors get to ask. No, I think it's not. Maybe it's not a good question. Because I got no responses here. No guesses. The simplest way that I can tell you that a particular location in memory is an instruction is that the program counter points to it. But the truth is that's not a guarantee because you can screw the program counter up and it's just pointing off into garbage. And then it takes off and it executes the garbage and then your whole computer crashes. So they're actually not really a great way to know, honestly. But it is all context. It is kind of social contract. It's whatever the programmer decided. Okay. Everybody still there? Is this mic on? Is this mic on? Okay. So let's talk about, all right. Texas is here. We can go. We can keep moving. Um, Here's the thing. In every computer instruction, yeah, thank you. All those that want to just join into this message here, feel free. We'll find out how many of you are awake. Uh, obviously you could be like just coasting or muted and watching The Office, uh, which would be pointless as attendance is not required, strictly speaking. Okay, every instruction in every architecture, in every von Neumann architecture, so every processor, every microcontroller, every, there's an opcode. Always, 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 there's an opcode. Opcode, what does it stand for? I don't know, operation code. Okay. And the opcode just is kind of like, what's the instruction? Yeah. Junlin, I'm so sorry. I am so sorry. Ah, I got off that stuff, you know? We should talk sometime. Seriously, we should talk sometime. That stuff just about wiped me insane. We'll talk, okay, Junlin? Compare notes. Um, seriously, as I come back online, I'm getting more social. See, you know. Anyway, opcode. Then the rest of it we kind of call operands, which is a fancy word that we use to simply describe the stuff that the operation works on or works with or uses, or it's like everything else. Okay. Now, in the LC3 architecture, the very first 4 bits, okay, they're the high order bits, they're on the left. Those first 4 bits are the opcode. Now, in other architectures, like on the ARM 64 Raspberry Pi, I don't remember. I want to say it's like 6 or 8 or something bits. Okay. Obviously, the more bits you've got, the more instructions you can support, right? Okay, here we go. Straight up question. Uh, you got 4 bits for the opcode. How many different kinds of instructions can you support with this architecture? I'm going to give you 4 bits for opcodes. How many instructions can you support? Ready, ready, go. 16, correct. That's it. That's it. You got 16 possible things. How many things do you want to do with a computer? Okay, hint, more than 16. So that means you got to kind of strip it down and make sure that you can build from that everything you want to build. 16 instructions, 4 bits for opcodes is a tiny, tiny, tiny number of bits allocated for opcode. It's microscopic. In fact, I think it's possible that if you went below, if you did 3 bits, that you literally wouldn't even work. I think it's possible that you can't get with 8 instructions. It might, but it might be actually too few instructions to actually build everything with. Usually we can take certain instructions, like for example, there is an addition instruction, there's an add instruction in the LC3, but there's not a subtract. Okay, what do you do when you want to subtract a minus b? Well, you've got to take b and negate it. And we treat it like, we use that as two's complement notation, right? So if we say these are two's complement numbers, which all addition in the LC3 is assuming two's complement notation, I can take the second one, I can flip all the bits and add 1. Okay, how do I flip all the bits? Ooh, there's a not instruction. How do I add 1? There's an add instruction. So and then I just add them together. So it takes me 3 steps, whereas if I had a subtract instruction, I could do it in 1 step. In the LC3, I have to do 3 steps because the instruction set is just so stripped down. Does that make sense? It makes just some things a little more cumbersome. That also speaks to potentially an advantage of trying to redo the class with a more sophisticated processor. The problem is there's so many other instructions that can potentially get in the way. We'll find out what I do this summer. We'll find out. Okay, that's it. So every opcode is 4 bits. We already talked about that. Yep. All right. Now let's talk about add. We'll just pick the first instruction we're going to talk about is the add instruction. And this is the thing you have to understand. Every one of these 16-bit instructions, it's like a coded message. You know what I mean? It's like you're passing notes in junior high school. And if I put, and if I write 7, then that means that we're meeting for lunch in the cafeteria on the north end. And if I say 3, it means that we're gonna leave school to go to the Taco Bell, or I don't know, right? I'm just saying it's an encoded message. What do these bits mean? They mean whatever we want them to mean because social contract. Okay. Now, the first part of this social contract is the opcode itself. So if the first 4 bits are 0001, then that's an add instruction. Now, by the way, again, if you had a random bit pattern of data or whatever, and the first 4 bits of that random thing was 0001, and you pointed the program counter to it, the control unit's going to look at that and go, oh, add instruction. And it's then going to interpret everything else as if it were an add instruction. So I'll stop using that counter example, but I just want you to know that that's kind of the way this thing works. From now on, I'm just going to talk about it's an add instruction and you know it's an add instruction and you want it to be an add instruction, not the weird pathological cases, okay? I know this is an instruction, I know it's in memory, and I know it's part of my program. And the program counter is going to point at it so I can pull this out into the instruction register and figure out what's going on. Okay, so step number one is the opcode, which is 0001. Then the next 3 bits is a destination register. Remember I said that in the LC3 there were eight registers. General purpose registers, we sometimes call them. General purpose registers, it just means they're nearby, you get to use them. There are special purpose registers like the program counter, the instruction register, the MAR down there in memory, the MDR over there in memory. These are registers, but those are special purpose. You can't do addition and crap with those, okay? The 8 general purpose registers, which are called R0 through R7, those you can do things with. For example, I can put it right here. So what this says is, I'm going to, whenever I'm done doing my addition, I'm going to put it in the register indicated by these 3 bits. 3 bits, how many registers can I represent in 3 bits? The answer is 2 to the third equals 8. So there's your 8 registers, okay? So if I said 000 right there in that destination register, then when I'm done performing the addition, I'm going to take the sum and I'm going to put it into register 0. If I said 111 right there, I would put it into register 7, okay? Whatever that number was, that's the register that I'm going to put it in, okay? Then the next thing I'm going to do with the next 3 bits is identify a source register, and that means, and we call that SR1, it just means the first source register. And that just means like the first operand. So it's going to be whatever's in this register right here that you indicate. Now, it's same exact thing. If I say 000 right here, then it's going to go grab the value in register 0, and it's going to give it to the arithmetic logic unit, the ALU. It's going to give that value out of the register into the ALU. And then it's going to grab a second value. Now, here's where it gets a wee bit tricky, which is the next bit in this encoded message is going to tell me whether the second operand for this addition, the second number, is also in a register. And in that case, I make this bit 5 be 0. Okay? So if I know that it's an add, and I see that there's a 0 in bit 5, then I know that my 2 values are coming out of registers. Oh, and by the way, none of these have to be different. It could say, take the value in register 1, and then take the value in register 1, give those to the adder, add them together, take the result, and put it in register 1. You could do that, which would have the effect of doubling register 1, right? So it could be, every one of these is sort of unique, and it can be, and any one of these 3-bit values can be any of the 8. Okay, that's what happens if bit 5 is 0, and by the way, when that guy's 0, these 2 little bits right here, they just don't get used. And by definition, they just get set to be 0 because that's what the circuitry wants. There's really nothing more magical than that, as far as we're concerned right now. There's probably a little bit of reason why it makes a little better sense than 1s, but it doesn't really matter. Think of them as reserved and they don't matter, but you make them 0s. Now, if bit 5 is 1 instead, Then, okay, this is the one we just did, right? When he's 0, then that's going to be another register. But when it says 1, then these 5 bits. Now, by the way, this whole opcode DR, SR1, SR2, these are just little reminders, little hints to remind you of what these fields mean. There's nothing special about those other than trying to give you a little bit of a helpful hint, to remember what they are. The IMM5 stands for immediate 5, meaning it's what we call an immediate operand, and it's 5 bits, okay? And it's a 2's complement number, meaning that this 5-bit number is viewed as a 2's complement notation. So it has a sign. It could be positive or negative, okay? So let's do a little quick review. I got 5 bits for a 2's complement number. What's the biggest magnitude negative number? The most negative number. And what's the biggest possible positive number? What say you, friends? Texas, nope, nope, nope. Hang on, I gotta, nope, so close. Josh, so close. Matthew, so close. So close. Matt, so close. Everybody's wrong so far. Barely. Everybody's barely wrong in slightly different ways. Junlin for the win. Yes. Yeah. It's -16 to +15. That's the range. Okay. Junlin wins the chat so far. We'll see if anybody can, pull off a conquering hero move by the time we're done. But for now, Junlin wins the chat. Okay. And the thing is, okay, look, you got 5 bits. So it's negative, 4 bits of magnitude, ballpark in that thing. And it's positive 4 bits. So if all these go on, right? If I go 0 and then these 4 are on, I know it's a positive number. At that point, I just, interpreting that, it might be a 2's complement number. But if the first bit is 0, it's positive. So I already know it's 15. It's just 1 plus 2 plus 4 plus 8. 8 and 4 is 12, plus 2 is 14, plus 1 is 15. So positive 15. And you might be going like -15. Oh, wait, no, that's right. We got an extra negative number, -16. Boom. Wait, Junlin, what is the relevance of that question? I don't know the relevance of your question, Junlin. We'll give you a minute to clarify. Oh, that's what happened to everybody else? Everybody's busting it, but you got credit. Is that what it is? No, everybody, and here's the thing too, right? And Noah did slip in that -16 there, just ahead of, under the wire. Um, but no, I really appreciate, there's Junlin did win the chat, but I really appreciate and value everybody. Just take a stab. I don't care if you're wrong. If you're trying, and even if you're coming up short, you're engaged. You know what I mean? You're doing stuff, and you're giving your brain a better chance to latch onto to the process. Okay, so please. And there's also no way to win the chat unless you take a chance on it. Okay, so that's an immediate value. What that means is I've either got to get a value into the register for the second number, but I can also hard code a value. Like if I wanted to flip all the bits and add 1 in order to negate a number, for example, well, I could use an immediate value of 1 for the second value, right? Take a register, add 1 to it, and put it back in that same register. Boom, I just incremented it. I can do those kinds of tricks, but I can do this either way, okay? So I'm going to move off of this. We're going to come back to this, and you are going to see this thing in action. And before very long, next week probably, I'll start showing you the LC3 simulator. and showing you this live. Make an instruction, put it in the simulator, and then run it. Okay. I want to just kind of do a little bit of a sort of introduction to different kinds of instructions right now, but we'll come back to it and drop into the simulator. Okay. All right. And please, stop me, interject if you have questions, of any type, right? So Texas, would it be negative 2 to the n to positive 2 to the n, where n's the number of bits? Well, run the number. If you run the number yourself, the number of bits we're saying there's 5 bits. Okay, 2 to the 5th is what? So you can validate this yourself, Texas, right? If you go 2 to the n and n is 5, what do you got? Negative 2 to the n. When n is 5, what do you got? Negative what? No. 2 to the 5th is 32. Yeah. Yeah, no, it's all good, right? 2 to the 5th is 32, 2 to the 4th is 16. So then you can look back at what Walter just dropped in there, which is 2 to the power of n minus 1. That's the negative extreme. And then to get to the positive, it's that same 2 to the n minus 1 minus 1, the whole thing minus 1. It's really hard linear notation like that, right? I mean, I think what Walter's written there is correct, but when you read that linearly, it just seems, you know what I mean? It's easier to see it graphically. Okay, let's do another one. Let's do another one. How do you load a register? Well, turns out there's a number of instructions that you can use to take values and to put those values into registers. So you can do stuff like addition. Okay, there we go. Sorry, I just saw who dropped that one. Yeah, Texas dropped it. Right, right. Except, yeah, yep. That's where n is 4, right? But if you do that thing with n minus 1 in the exponent and n equals 5, that's really what we're doing, right? With that sort of munging that and assuming that it's a two's complement notation. N is really 5 because there's 5 bits. Yes, exactly. Exactly. Matthew, thank you. Okay, sorry, Junlin, I think you've been overtaken by Matthew for winning the chat. I think it may be a separate category, but that's serious for the win right there. Um, okay, let's talk about LDR, the load register instruction. Okay, it's got an opcode, just like always. There's an opcode, and in this case, the opcode happens to be 0110. Yeah, why? I don't know. It works. Good enough, you know? And it turns out that this one, we're not going to drill all the way down. I just want to show you a few different kinds of instructions, okay? There is a register. The DR is always the destination register. It's where stuff's going. Where's it ending up? That's the destination register. And in this case, let me see. Yeah, nope. And then in this case, there's a base register right here, these 3 bits, and then there's an offset. And in this case, what actually happens, again, don't worry about this right now, just giving you a feel that there are these different kinds of instructions. This instruction takes a register that you give it that has an address in it. So you got to get an address into that register. But once there's an address in the register, it takes that, it adds a 6-bit offset to it, which could be positive or negative. It's a 2's complement number. Adds that, goes out to memory to that location, pulls the value out of there, and puts it into the destination register. Okay. All I'm trying to show you here, you don't have to remember LDR at this stage of the game. Just remember that every one of these different opcodes has a different recipe, okay? And how do you remember? How do you figure all this out? Well, a couple ways. If you have the book, there's documentation for this instruction set in the book, all right? If you don't have the book, I have pulled just that documentation out, and it is on Canvas, okay? And it looks like this right here. Okay, now the front of it looks like this, overview, the instruction set, and it just reminds you of some things about the architecture. And it tells you a little bit about how the memory is broken up, kind of a memory map, and then it tells you just some other things that will all make sense, believe it or not, in the next 7 weeks. And then here comes the instruction set. Just notation to remind you again, so you can look stuff up. And then boom, here you go. There's the instruction. There's the add that we just talked about. There's the LDR, and then this is sneak peek. There's an and, a branch, a jump through subroutines, other load instructions, a not, and other stuff that feels very mysterious at this point. Okay, and then here we go. There's the documentation for the add. And there's the encodings. That's what the bits look like, okay? That's just what we barely did. And then some description of exactly what happens, and then a text description of what's going on. And then when we get to assembly language, what the assembler wants, what the assembly instruction stuff looks like when you're actually writing the code in assembly language instead of in binary, in bits. Okay? All right. So that document is your happy friend. Okay? Now, here we go. Back to the fetch, decode, execute cycle. Okay? We're gonna work this thing down. I want to just see real quick how close we are. There are 60 slides total. Yeah, we're actually fairly close. I don't know if we'll get all the way through. We might, given the time today. Okay. So this is what we do. And it turns out that fetch, decode, execute, and you're like, well, Dr. K, there's six of these steps. Yeah, fair enough. This is just kind of breaking them down a little more granular than that. I do fetch by grabbing the instruction out of memory, okay? I do decode because I've got to figure out what it is. Then then here comes execute. Well, evaluating the address is kind of like kind of part of decoding, getting those operands, getting everything ready. You're kind of, maybe they're more like executing, but we execute. We do what the instruction says, and then we store the result away if needed. And every one of these takes multiple clock cycles. Remember, every time the clock pulses, that's like you turn the crank once on the machine, turn the crank, turn the crank. I just realized the most amazing thing. I have a machine that I built that actually is almost a perfect illustration of the clock, and it just occurred to me, and it's sitting upstairs. I can go grab it. I have the headphones are portable, but I might do that. I'll bring it down here and have it either at the end of this class or maybe next week. I don't know. Depends on everybody wants to see it. Should I do it now, or should we lecture a little more and then I go grab it? No, I'm gonna go get it now. This will not take long. Hold tight. I will be returned. And I'm still with you. I'm just out of sight because I'm heading upstairs to grab the machine where it lives. I think you're going to like this. I really do. And
Wait,
the
what
machine.
model are we on right now?
Walter? What module are we on? Like 5?
Cool.
I think it's 5. Can we get a confirm or deny from somebody on that?
Yeah, I'm pretty
Yes,
sure it's 5
module
because we
5.
Feels
had,
like it. Feels like, and
yeah.
we're wrapping up. So we should be pivoting. Okay. Can you see this? Now I've got to try to figure out the camera angle on this thing. This is uncharted territory here, okay? In the history of this class, it's uncharted. But this is, okay, can you kind of see that? You can see it, right?
Yes.
Yeah,
Is
we
that
can
coming
see.
through okay? Yeah, okay. All right. Yeah, this is an unusual thing, okay? So here's the deal. We got all the little marble units, okay? So imagine, so here's the little crank. So imagine that you said the clock pulses, boom, clock, that's one clock cycle, one clock cycle, one clock cycle, one clock cycle. And that's like electricity dissipating through a circuit. Flip-flops are settling out, one clock cycle, one clock cycle. See what I'm going at? Isn't that cool though? Isn't this cool? I built this with my own bare hands. And then boom, something cool happens. Okay, was that worth it? Was that worth grabbing? Uh, that's it. But it really is. But I mean, seriously, the whole circuitry thing. I mean, you move one, and people are, the balls are kind of representing the flow of electricity, right? Signals that are, a line goes high, you know what I mean? Line goes high, line goes low, and then there's some things that just take a little bit of time for the electricity in the circuit, right? To kind of like the flip-flops, right? Where it's got to like move through until it gets happy. That time frame has to be smaller than the clock pulse. So it settles out and then we can crank again. But now imagine this dramatically more complex machine. Um, and yeah, anyway, I don't know, when did I build this? Christmas? Yeah. You can get these. It's a kit. I mean, I didn't invent it, which would have been extra amazingly special, but I did build it and from scratch. I had the stuff from the kit, but I mean, it's still just like one of the coolest. Think of it as a puzzle if you want, but it's a very cool puzzle. And I'm probably going to get distracted now that it's at my desk here. I try to keep it upstairs where it's kind of something that a curiosity for guests to come fiddle with, for grandchildren to break, probably eventually. Okay, that's it. Okay, so I hope that was worth it. And what do we got here? Yeah. Oh man, and I've seen that. I've seen that marble machine. I've seen this video. Thank you, Texas, for dropping that video. Yeah. Okay. Yeah. There we go. So it's now just like happily sitting over on that part of my desk. But that really is, I think, a visual of the clock. It really is, because every time the clock pulses, it's like energy goes live, and it's put energy into the system, and it just moves everything forward one little step, you know. And so when you access things like, accessing memory, remember when we went through all the steps and the lines went on, you know what I mean? And then then that address went live and then the write enable and write every single one of those little steps that we walked through on that graphic picture of memory was a clock cycle. And so instructions take different numbers of clock cycles. There are some instructions, like if you have an architecture that has like a multiply instruction, super convenient to program, you understand that takes a lot more cycles than, say, an add or a not, right? I mean, all of these different instructions take different numbers of cycles. And LC3 won't tell you this because it's all simulated. But if you have real hardware, it will literally tell you how long. Either in well, it's usually the clock speed is when it says so many gigahertz, so many whatever, right? That's telling you what the clock speed is, how frequently the clock goes boom, boom, boom. So if it's gigahertz, that's a billion times a second. Okay, hertz meaning a cycle per second. So gigahertz is 1 billion pops per second on that clock. Crazy, right? I mean, almost, for me, really kind of incomprehensible, frankly. And maybe for anybody, really, I can accept what it is, but I can't imagine how that really is a thing. You know what I mean? Because physics. Yeah. Okay, but they will tell you typically how many cycles it takes, how many machine, internal clock cycles, and then you can actually figure out how long an instruction takes by looking at the clock speed and then the number of cycles, which is the number of clock ticks. I mean, you know what I mean? Times the number. What am I trying to say? The clock speed is how fast, and then the number of cycles is how many ticks. Multiply those together. I now know that this one instruction is going to take me zero point 0.7 microseconds or something. You're like, okay, why do I care? Well, because if you're going to do something billions and billions and billions of time, maybe there's a slightly faster way to do it down in the hardware. That's going to make the whole thing be a little bit faster. And it aggregates out. Okay. Okay. There we go. That was an unexpected demo, but it makes me happy, and I hope it made you happy. Okay, we're gonna break these down a little bit more. How are we doing on time? Oh, we're killing it on time. Okay, we're doing great. Um, okay, the fetch. What the fetch? Um, is that only a Utah expression? Do other people in the English-speaking world say fetch the way we do in Utah? Just curious.
How do we say it in Utah?
Oh, just as a swap out for the F word, basically,
Oh, I
like
didn't
what the
think that.
fetch? That's a thing.
I'm from LA, so we
Well,
didn't
there
use
you
that.
go.
Fetch is
Yeah.
normally like a dog catching a stick or something, like playing fetch. So we
Okay.
usually just say the actual F word in LA. So yeah.
That's right. Yeah, I think in Utah mostly, I don't know. Some of the, come on, locals help me out. Uh, I think it's yeah, Texas, you just swear. I don't know.
I know
Anyway,
that in Mean Girls it's a thing, but
what is fetch or the F word?
fetch, fetch. Well, the F word, it's a PG-13 movie, so you can only say that once in those, right?
Yeah,
So,
right, right. I think
but
it's two
they
now.
use the word fetch because she's trying to make it all popular and stuff, but she's
Oh,
like,
so she
stop trying to
uses.
make fetch popular. Yeah.
Okay, all right. A movie I
It's stupid.
A never have seen. B, you know what's coming next, right? I just don't ever see myself watching that
Probably
movie.
won't.
I just don't see it
Yeah.
ever happening, unless there's some other.
Well, it's one of those like coming of age movies that you watch when it comes out, but you probably wouldn't be interested in it if you didn't see it when it
If
came
you're
out.
already of
It's
age,
also
right?
hilarious. Yeah.
Yeah. So I'm. Yeah. Then you're of age, and then you're what am I? Past age, overaged. I don't know what I am. Aged,
Just aged.
aged. Yeah, yeah. Aged like a fine cheese or a fine wine. Okay. Okay. Let's move on, shall we? It all started when I got distracted by fetch. Okay, we get the next instruction from memory and we load it into the instruction register. Now, here's what's actually happening underneath. And this, again, believe it or not, is going to be a little more second nature. Just don't bail on me, okay? Don't bail and you won't fail, okay? Here's what actually happens. We have to take actually, I'm going to go right here because this is the steps right here, these four right here, but I'm going to put them over here and just kind of walk you through this real quick, okay? And again, I'm not going to expect you to like remember this and regurgitate this on one of the module exams or the homeworks, but I want to just say it so you can see, much like my little cranky machine over here, so that you can see kind of what's going on. Okay, so there's the MAR down there. There's memory right down in this corner. I'm pointing at my external monitor, which you can see here on the stream, but for me, it's right over here. I've got to take the PC, that's the program counter. that holds the address of the instruction in memory. So I got to put that PC out here on the bus. It's on the bus is just a wire, so it's like joink, and it's like live everywhere on the bus, right? Then I got to pull it off the bus down here and put it in the MAR. That's the first step. Then I increment the PC. I increment it right now. That's this little +1 right here. But I increment the PC so that I'm ready to go with the next instruction. Okay? Then I take whatever the word in memory is down here that the MAR points to, I pull it out and I put it into the MDR, which is the data register, the memory data register. Then I take the value of the memory data register, put it back on the bus where it can be pulled off, input into the instruction register. Whew, that's right. That's a crap ton of work just to, you know, just to fetch. Yeah. But I just wanted you to get a feel that the machine is doing all those things, right? Just like if you were watching carefully, right? There's one step where the ball like moves through the thing and goes up there, then it has to like, go up 1, 2, and then on the third one, it actually drops. There's multiple incremental steps to get you to this sort of result. Okay. All right. Then we got to decode it. Fetch, decode, execute. That's the cycle. Um, and yeah, remember decoders? Literally, it's a decoder, okay? It actually is that the opcode triggers a line to take off uh, a Rube Goldberg machine. It just triggers it to take off and go um, for the circuitry in the control unit, which we're not going to get into because that's just another level of grunge, okay? We evaluate the address. We don't always have to evaluate an address, right? But, if we have to, then this is when we would do this. Sometimes we got to calculate an address, like LDR, where we had to take the base plus the offset and do a little something to figure out like where are we going to look, okay? And then here comes that LDR as an example, which I just threw it out there. I don't really care. We're going to move past that. All right. So this is just to illustrate the idea of when we do the fetch, um, we talked about LDR as an instruction and we talked about add as an instruction, right? With the LDR, I have to do these various steps like load the MAR because we calculated the address, load the MAR, read the memory into the MDR back on the bus to the destination register, right? And that's what I do in the LDR with the LDR instruction. With the add instruction, I pull the operands out of the registers, right? One of them, you know what I mean? It's just to help you understand that the different instructions make the machine do different things underneath. That's really the main punchline of all of that. Then when it's time to execute, I got to do whatever the instruction is trying to do. In the case of the LDR, there's not really an execution phase. Once I've got that value, I just store it into memory. But the add, there is some stuff I got to do that's the actual addition. And that's done in the ALU, which again is the arithmetic logic unit. And then I got to store the result when I'm done. Boom. That's it. Rinse and repeat. That is the whole dang thing. And since I incremented the program counter when I was just, as soon as I started doing stuff, I incremented the program counter because frankly, it's like free cycles. While everybody's waiting to do all the other crap, I might as well just flip the program counter. It'd be amazing. I just realized something truly amazing. A wood puzzle like this, using the silver marbles, as representing electricity and build like an adder, that would be freaking awesome. That's true. That'd be amazing. You could build the entire LC3 as a wood puzzle. It's never going to happen, but it would be amazing. All right, that's it. That's it. I mean, that's the fetch, decode, execute cycle. Now, the PC already has the address. If there's nothing crazy happens to the PC, it just goes to the next one, the next one, the next one. That's the default. It turns out, spoiler, we can actually change the PC in the middle of the whole thing. We could say, hey, I know you already incremented the program counter, but I want you to just put this value in the program counter instead. Okay? And we will call that a branch instruction or a jump instruction. All right? What does that enable us to do? Everything. Like decisions, right? I can make if statements, right? Because there's a point where you've got to be able to go, maybe I want to just go down and do the next thing, or maybe I want to skip it. Well, to skip it, I've got to change the program counter to be here instead of to the next one. Well, I've got to have the ability to change the program counter. Some of the instructions, in particular, branch and jump, I can change the program counter. That allows me to do conditional statements like if then else, and it allows me to do loops. Decision making basically can now be built in. Oh, yeah. And that's really, really cool. So that's kind of what this is about right here, changing the sequence. Okay. And this is, again, we got like 5 slides, and I think we're going to get through it. And then we'll be done with module 5. And then Walter and Zach will like make sure we change, fire up the deadlines and have everything be due on Saturday. And that, again, everybody knows you can do it whenever you want to do it. And after that, and multiple times and all the rest of it. But that just makes it turn into a 0 on Canvas to remind you that you're not passing the course if you're not doing these things. Okay. All right. So there's a bunch of things you can do with just purely sequential execution, right? But you got to have the ability to do some other stuff, and we call those control instructions. The add instruction is an example of what we call an operate instruction, which is a clunky. Calling it an operate instruction is kind of clunky. The load R, we call it a data movement instruction. It just, so, operate instructions like do operations like adding and subtracting if you have that, doing a not, doing an and, these kinds of things. Data movement allows you to like just move data from a register out into memory, or go out to memory and get values and put them into registers, that kind of stuff. The control instructions allow you to make decisions. All right. And in other words, it changes the sequence. How do you change the sequence? You change the program counter. Because if you don't change the program counter, it's going to just increment, bit, 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 bit. But if I just somewhere here, I change it, you sneaky just go in and just go, oh, hey, program counter, you're over here now. And then you're like, okay. And then the control unit goes, okay, fetch. And the program counter is pointing over here, fetches that instruction. It doesn't care. It fetches whatever the program counter is pointing at. So by just change, this is like cool magic. Just by changing the value in the program counter, you can change the flow of the execution of the program. You can go over to subroutines like function calls. You can jump over somewhere and come on back. You can, loop until some condition holds and then drop out. You can do all the cool things. Okay? And isn't that cool, really? Is it just me? Hang on a second. I need to run my machine for a minute to just see if it's still cool. Machine still very cool. Okay. But even more magical is this idea that that all we had to do to jump around and change the sequence was just change the program counter. It's like so simple. Like, why didn't I think of that? Oh yeah, because I wasn't born when that was invented. That's probably why. I was not born when that was invented. Okay, so that's a long time ago. All right, so here's the deal. I already did that. I already did the slide. That's the deal. Hang on, glasses. So Alex just asked, so basically we know if the bits are code or not because of what's pointing at them. Yeah, in particular, the program counter. If the program counter is pointing at something, it doesn't matter what we thought it was before. The control unit is going to treat it like an instruction. You're going to go, look, you point the program counter at it at the time that I fetch. Our social contract says that's an instruction. Okay? All right. Okay. Wait, where am I? Right here. So let's give you an example of these. And we're going to break all the instructions down, okay, in greater detail. But for now, let's give you the jump instruction as an example of a control instruction, right? Branch is another one. But we'll just do jump. The name of it, we call it JMP, jump. JMP pronounced jump. It's got a unique opcode, 1100. Why? Social contract. Well, all the jump wants to do is you give me a register that's got an address in it, and I'm just going to just go there. That's it. Okay? So what is really happening? What's really happening, and by the way, this reserved, don't care, don't care. To do the jump, I literally only need 3 bits of operand. And those 3 bits are going to tell me what the base register is. That's it. And in the base register is the address of the spot in memory that you want me to jump to. Boom, that's it. So what is really going on? What is actually inside the machine when this instruction runs? Who can confident? This is going to be the last round of winning the chat, I think. No, Junlin, no, you do not need to memorize the opcodes. Thank you for asking that question. Every module exam that from this point, right, as we start to get into instruction sets, all of the opcodes are in the Canvas exam. Okay, all the opcodes are there. So it's basically open book on that documentation. So that appendix that I showed you earlier, that entire document is in, at the end of every Canvas module exam. And when we used to do this live in the lobby, we always had like hard copy papers where we just like give you that like a packet, and the exam. But now that we do it on Canvas, but okay, last chance to win the chat. What is the control unit going to actually do? I know you can figure this out from everything we've talked about. Yeah, it is. Yeah, you're on the right track, Alex. It is kind of like but copy what to paste where. What are you doing? What's happening? Come on, you know you can do this. I know you can do this. I'm waiting because we got time, and there's only one more slide, and I already know what it is. Come on, Gabe. Come on, Gabe. Or Alex, you're going, man. Alex, you were like heading in. Oh, can you get the question again? Gabe, get out of the hot tub, man. Okay, listen, here we go. I'm going to give you the question again. Blame it on the dog. Do not blame it on the dog. Okay, Gabe. The question is, when this instruction runs, what's the control unit going to actually do? Like tangibly, what if you were given this instruction with this information and you were the control unit, what would you do? And get distracted by your dog, I'm sorry, Gabe, is not one of the options. There's no clipboard, Derby. There's no clipboard per se. Alex says, make the base register match the reserved register. Now, we're getting closer. Also, there's no such thing as the reserved register. You got to name that bad boy, okay? That reserved register, of which I believe Alex speaks, has a name, and we have been using that name of that special purpose register. What is it? And what does it mean to make something match? Ooh, ooh, ooh. What is that? There's no register of execution. Josh, what are the terms? Come on, I'm waiting, man. We got time. I'm waiting. I you I want you got to get precise. We got to go to precision, okay? Because I think you're feeling the feel of it, and that's great. The feel is there. Okay, there's no destination reg. Well, there is kind of a destination register, but it's implied. So Junlin said destination register. There's no destination register in the instruction, but there's an implied destination register. What is it? What is the implied destination register? Josh, okay, yeah, Josh gets a half a victory on winning the chat. The program counter, okay? Now, so there's a value that's going to get shoved into the program counter, not MAR. Derby, not MAR. The base register holds the address that I want the computer to execute next, okay? No, not MDR. So this is good. This is good fun. Keep going. Josh already won half this. The destination register is the program counter. Where is the thing coming from that's going to go there? And it's actually a little tricky because Derby and Josh, it isn't the MAR and it isn't the MDR and it's not from memory. I mean, that's a good guess, but no, it's not coming out of memory. Kermit the Frog is not sure. And he's very nervous. Alex is correct. Alec wins zero point 0.2 chat victories for Kermit the Frog, accurately reflecting pretty much the spirit of the entire class right now. But not a solid victory, okay? Come on, come on. You can do this. Nope. Josh, I love the guy. And by the way, Mondo, everything. Okay, Gabe. Okay, you ready? You give? Do you give? Say, Uncle. Um, it's an exercise. Yeah. Oh man. Okay, so here we go. You ready? And I did say this, but I'm going to say it more clear now. That you've had a chance to noodle. What that does is it prepares your brains for the truth. You noodle on it, and you're like coming up short, and then it's like, okay, here we go. Here's the real thing. You're primed for it. The base register holds an address. You put into the base register the address of where in your program you managed to somehow, prior to this point, fill that base register with an address, and it's the address of where you want your program to run next. All this instruction does is it copies the contents of whatever the register is that's articulated in these 3 bits of the base register. So if I said 101, which is 5, it would go to register 5. It would grab the 16 bits in there, a copy of it, and it would just put that into the program counter. It would just overwrite the program counter. Done. That's it. That's the whole instruction. You were also very close, moving around the surface, but not quite nailing it. Anybody want to vent on me now? Or anybody have anything they want to say about that? I hope that was not an entirely futile exercise um, trying to get you thinking about that. I did say earlier as I was describing it, but again, it's not written here. It's not, you know, So Josh asked, no, exactly. I have seen, I have seen this status that Alex has shared. I have lived that. Yeah. So Josh asked, so it uses the base register to get the data from a register and then puts that data into the PC. So what you're saying is it uses these 3 bits that we call base R, the base register. Those 3 bits identify which register. So if they say 0, it's register 0. If they say 5, it's register 5, right? That gives us the mapping. That tells us which register to go to, grab its contents, and put it in the program counter. And then we're done. What's the control unit going to do next? Fetch. It's going to grab whatever in the program counter, look at that as the address, and go out to memory and get it. Treat it like an instruction. That's it. Okay, so, yep, Josh. Junlin, 8. 3 bits, 0 through 7. And Josh, no, it's not coming from memory. It is already in the register. It is the actual value in the register that's indicated by base R, that 3 bits. It's the value. You don't go out to memory to get anything. Boy, I sure hope I have that right. And if I don't, we're going to fix it later. I suddenly was questioning myself. Yes, Junlin, repent of this. Do not forget the 0. The 0 is lonely enough. Okay. You know, you're not writing to memory, Texas. You're just changing the program counter. You're changing the program counter. Now, let me do something real quick. Just because we have a couple minutes, and I just realized I'm running from memory here. I realized that it's entirely possible that I may have just remembered slightly wrong, and I hope not, but it does happen, you know. Um, okay, no, I was right. Okay, good. Since I was right, I'll go ahead and show this to you. No, if I were wrong, I would definitely want to show this to you. Okay, there it is. Jump and ret. It turns out, don't worry about ret for now. Ret is simply the name we give to it when the base register is 7. And there's some reasons why, which we won't get into right now. Okay, check it out. You see what the operation is? You see what it does? PC gets base register, no memory access. Okay, the program unconditionally jumps to the location specified by the contents of the base register. Bits 8 to 6, right there, identify the base register. That's it. Then it tells you about the ret instruction being a special case of the jump instruction. That's the whole thing. You don't go out to memory to get anything. It's already in a register. Now, how did it get in the register? It had to have happened previously, right? You had to have put it in there, gotten it in there, mathematically created it. You know what I mean? You have to somehow gotten a value into that base register that is a legitimate address. Okay. I don't know. I feel a little wrung out, everybody. Josh says, so jump is like uh, jump is like, are you trying to say dereferencing a pointer? No, it's like copying a pointer. Copying a pointer and pasting it. Gabe, stay with me, Gabe. Gabe, we're losing you. Um, it's like copying a pointer and just handing that pointer from over here to over there. But yes, pointers and addresses, same idea. 16 bits that we can use as an address, that is exactly what a pointer is. When you get to stuff where you care about pointers, that is exactly what a pointer is. All right, Gabe seems to be looking like he's going to maybe pull through. Keep waiting for that thing, you know what I mean, for it to end, and he keeps pulling through. So I'm glad to see that. Time maybe 12:44. Okay. Alrighty, my friends. I hope that was good. I hope that you enjoyed that at some level. And then, oh yeah, very last, whatever. You do not have to remember this. I just wanted to show you. Remember that state machine we talked about? Yeah, this is it. This is actually it. Um, right? This basically says grab the PC, put it in the MAR. That's the memory address register. Increment the PC. Go out to memory pointed to by the MAR, grab the data, put it into the MDR. Grab whatever's in the MDR, put it in the instruction register. Now, whatever's in the instruction register, decode it. If it's an add, do this stuff. If it's a LDR, do this stuff. If it's a jump, just take whatever's in the register and put it in the PC. And everybody goes back to state one, which is fetch. That's how we fetch. Okay, time's up. Module 5 is done. Don't bail. Don't bail. Stay with me.
Thanks, Dr. K.
You're welcome. You're welcome. I'm
See
gonna
you,
just
see you next time.
I'm gonna wind this whole thing down here with a little bit of we need some exit music, but I don't really have what I need right here. But I'm just gonna wind it down while we for those that wanted to just they're dying to just see this thing roll one more time. And I'm gonna clock up
Did
the
you get that off of Amazon?
I don't know where I bought it. Possibly. By the
Because
way,
I
it's
bought like a treasure box from Amazon that has the same kind of thing.
yeah, I will tell you this, the brand, it was incredibly well done. The whole thing as a puzzle was incredibly oh, Roker, ROKR. That's the brand. You can kind of see that right there. That's the brand.
That's so cool.
It was amazingly well done. I mean, the quality of everything, the instructions were absolutely brilliant. I mean, truly, I'm going to go over here. Actually, I'm going to go over here. The actual instructions, the construction instructions were actually amazing. I'm going to crank up the clock speed, see if I can get a hardware failure. There is a certain clock speed where the balls will start to collide and, you know, being a former software tester, I can't help myself from trying to stress test a system, you know. That's it. This, everybody is so easily amused, including me. Anyway, yeah, oh, there's one that got loose over here. Okay, yeah, we just lost a ball. So, all right, yeah, I'd like to thank our sponsor, Roker. Not a sponsor, but I'm giving them a shout out anyway. It was actually a kick in the pants to build, and then just really satisfying when it was cooked. So, you know what I mean? Little engineering nerd moment for a holiday cheer. So, anyway, I'm out. I'm going to shut it down, and I shall see you all next week when we will launch Module 6. Later.